Hello, I welcome you all to this another interesting screencast. The problem reads, each member of the pin connected mechanism has a mass of 8 kg. If the spring is unstretched when theta is equal to 0 degrees, determine the angle theta for equilibrium. Set K equal to 2500 newtons per meter and M, which is the couple moment, equal to 50 newton meter. In this particular video, we are only going to be dealing with the first problem. We are going to work on the second problem in the other video because of time. Right, and this particular, both of course problems are coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have been asked to solve this particular problem, and we are going to use a method called virtual work method. Virtual work method is an alternative method to the equation of equilibrium method for a particle, for rigid body, for interconnected rigid bodies. So since this is an alternative, it simply means we are able to solve this particular problem by using the equations of equilibrium for a rigid body or for interconnected rigid bodies. So what is this virtual work method? It states that the total virtual work del U is equal to 0 in a system like this one, which is a system of interconnected rigid bodies. And this virtual work is due to, it can be due to the summation of the product of translation of forces and translation of virtual displacement del R. It can also be due to couple moment product of a couple summation of a product of a couple moment and rotational virtual displacement del theta, and when we sum up all these virtual works, they equal to 0. So given a force F and given a translation of virtual displacement del R, for virtual work to exist, the two must be collinear or parallel, and if they are in the same direction, then we have positive virtual work, otherwise we have negative. We can also have a couple moment M and rotational virtual displacement del theta, and for virtual work to exist, the two must be collinear or parallel, and if they're in the same direction, then we have positive virtual work, otherwise we have negative. So in a nutshell, this is what virtual work method is. So like we said, we are only going to work on the first case. We are going to solve the other case in the next video. So we'll call this one as case 1, which is 11-13. Alright. So first things first, we are going to draw the free body diagram. So we have at the hinge D, going to have a reaction like so. We'll have another reaction like so. At A, we'll have a reaction like so, and we're going to have another reaction like so. And we have also the weight of each particular member. We've been told that each member has a mass of 8 kg, so convert that mass into the weight. Alright, so let's label this. So we have, this is AY, this is AX, this is DY, this is DX. We'll call this just W, W, and W. And we do a section of this particular spring, and we expect the spring force, okay, like so, and like so. Okay, and let's call this spring force as Fs. And then let's apply a vector displacement, which can be translational or rotational. All right. For us, we are going to go with the translation one, and I'll apply it. You can apply it at any point. It's really up to you. You just have to maintain the joint configuration as the system gets deflected or displaced. So if I applied a vector displacement at point C in the vertical direction like that, all right, then we are going to have a system like so. Let's say we have a system like so. Okay, I think this is much better. It's thicker. We'll have a system like so. Okay, something like so. Okay, let me use this. Something like that, and then something like that. This is good enough, I think so. All right, there we go. So we have something like that, and then of course at C also we have a movement in this direction. We do have a movement in this direction as well. Okay, and then at this point, let's name this point. So let's call this point, that's D. So let's call this point as point E, and I'm going to call this E. So let's call this as E. We call this also E, and then let's call this point as F. Okay, so let's do so. There we go. So we'll have a vector displacement like so, and also in that direction like so. So we'll have another one in this direction like so. Okay, and another one, another movement in this direction like so. Okay, and also the same there, we'll have a movement like so, and also a movement in that direction like so. Okay, so I think this is and then we are going to have also at this point we have another movement at this particular point like so. This is okay, so let's label these. So I'll just label those that are going to give us virtual work. They must have virtual work collinear to a force. So this one we're going to label it as del YF. This one we're going to label it as del. This one is del. This is del YE. Okay. This is del YE. Alright. And then this one is del theta A. Alright. Of course, even the other one there is del theta D. I'm not going to label that. I'm just labeling those with that are going to give us the virtual displacements. Okay. What else? So we have, let's now define our fixed. So let the fixed reference be A. Okay, so let's define now our spring force. So spring force is just going to be equal to K times S, the spring constant times the stretch. and we know that K is nothing but equal to 2500 newtons per meter, and we know that S is just equal to L final minus L original, or L node, and we know that L node at theta is equal to 0. The spring is unstretched. Of course, it will have this initial length, which will still clear out or subtract once we subtract L final minus L node. So we can safely say L node, we can safely say is just equal to 0. Okay, for now. All right. If you want to, of course, you can say it is just L plus 0. And the other one, L final, will be L plus something, but the L's are just going to cancel out. So it just comes back to 0. Okay, just 0 meters at theta equal to 0 degrees. All right. Therefore, Fs is just going to be equal to 2500. Of course, I've not defined yet what L final is. L final is just going to be equal to, that's the length, which is just equal to the length of our member. What's the length of this? 300 millimeters, which is just 0.3 sine theta. Okay, Fs, so we are talking about this length here, this length. Okay, this is the length we are talking about, which is just 0.3 sine theta. Getting it right? All right. Right. So then the spring force is just going to be equal to 2500 times L final, which is 0.3 sine theta, minus 0. Okay, so this just gives us what is this? That's 2500 by 0.3. This just gives us a 750. Okay, sine theta. All right, let's define now the positions for E and the F and B, okay, in the vertical direction. All right, so let's start with E. We can say E, we can write it this side, so we can say from here to the point where E is, which is just half the length, let's say up to somewhere there, okay, so there we are. So this is our E. So this one, maybe this one, this A here, we give it another letter because it will have a difference. So this is EF, let's call this one as G. All right, so there we go. So this we can call it as YE, okay, and then let's define this other length here. From this point we define B, okay, we define B like so, there we go, and then from this point here we define F, okay, then from this point to this point we define G, okay, all right, there we go. Okay, so let's label this. So we have this one as y b. Of course, at b here we are also going to have a vector displacement in this direction like so. Okay, we'll have also in that direction like so. All right, and this one we are going to call it as del ib. Right, and then we have this one which is y f, and then this one we have y g. Okay, so here we are. Let's now define this particular each one of these particular position. So let's start with ye. So ye is just going to be equal to half the length of the member 300, which is 1.5. I mean 1.5, 0.15 rather. Okay, sine theta. Therefore, its the vector displacement is just going to be equal to del ye equal to 0.15 cos theta del theta. Then we have the next is yb. Yb is just equal to 0.3 sine theta, and then its vector displacement del yb will just be equal to 0.3 cos theta del theta. The next one is yf, and yf is just going to be equal to yb plus half the length, which is 0.15, and the vector displacement del yf will just give us 0.3 cos theta del theta. Then we have yg, and yg is just going to be equal to, so we do have the length, this length here, which is just a 300. So it will be a 300 plus half this length. So we have a 0.3 plus 0.3 plus 0.15 sine theta, and therefore del yg is just going to be equal to a derivative just 0.15 cos theta del theta. So we have everything, and then we also have del theta a, which is just equal to del theta. All right, so now let's now feed all these equations in our vector work equation, which is del theta is equal to 0. So at point A, both the rotational vector displacement is in the same direction with our moment, and they will have therefore a positive vector work, so it will be m del theta. Okay, because del theta A is just equal to del theta. And then at E, they are in the same direction, so we have positive vector work, so it will be w del ye. And then at B, they are in the opposite direction, so we have minus, so that is fs del yb. And then at F, they are in the same direction, so we have positive w del yf, and then at g they are in the same direction, so we have positive w del y g equal to 0. Okay, so there we go. So we have this equation. So now let's enter everything else that we have. So m, we have m. Let me take it up there. We take it up. So I bring this here like this, this, and this. Okay. So what is our m? Our m is 50. So we have 50 times del theta, so which is just del theta, then plus w. We said w will just be equal to 8 times 9.81, and this gives us 8 by 9.81. This gives us a 78.48 newtons. So this is just going to be equal to 78.48, okay, times del ye. Del ye is 0.15 cos theta del theta. Then minus fs, we said it's just a 750 sine theta, and then this times del yb. Del yb is 0.3 cos theta del theta, and then we have a plus w, which is a 78.48 del yf, which is just equal to 0.3 cos theta del theta, plus we have w again, which is just a 78.48 del yg, which is just a 0.15 cos theta del theta equal to 0. So if we factor out del theta, okay, we are going to have a 50 there like so. Alright, and then let's sum up everything. 78.48 by 0.15, and then we have plus 78.48 by 0.3, and we have plus 78.48 by 0.15. So we have a plus 47, a plus 47.088 cos theta. Okay, then we have minus 750 by 0.3, so this just gives us a 225 sine theta cos theta equal to 0. Alright, so we know that this is not going to be equal to 0. The only part that will be 0 will be this part. Alright, let me just go through again this one. 78.48 by 0.3 by 0.3 by 2, 47.088. Okay, it's fine. So then let's work on this part. We are going to use the numerical technique. So we have a 50 plus 47.088 cos theta minus 225 sine theta cos theta equal to 0. Alright, so using the numerical technique, I'll represent this as just a function of theta equal to 0, and then I will have the domain from 0 degrees to 90 degrees. Alright, so imagine we are on the number line, the solution lies at the point where we have 0. So we need theta that will give us the function equal to 0 and theta that will give us a function equal to positive, negative and positive. Then we start doing the iteration so that we get closer to a solution, like so. Alright, so let's begin the work. Where are we? Alright, so we may have more than one solution there, but we are only going to find one. We may have more than one. We're just going to find one solution. Other solutions, you can always check them. So we have the function and a theta, the independent variable, and then the function, the dependent there, which also acts as an error. So let's plug in 0 there, like so. Plug in a 0, then we feed in a 0. What do we get? So we have a 50 plus 47.088 cos 0, of course. This is just 97. The other part there is sign there, so that part becomes a 0. So this is 97.088. Okay, let's plug in a 20 degrees. So it's 50, 47.88 cos 20 minus 225 sine 20 cos 20. Alright, this gives us a 21.93. Okay, let's try and plug in a 30. So we have 50 plus 47.088 cos 30 minus 255, I mean 2, let me check the first one. 50 plus 47.088 cos 20 minus 225 sine 20 cos 20. 21.93. Okay, that was fine. 30 degrees. Again, so we keep on checking until we find a point where we'll have one negative. Okay, they are just all positives. Okay, they are moving in the same direction. So 50 plus 47.088 cos 30 minus 225 sine 30 cos 30. So this gives us a minus 6.65. So we know between 20 and 30 the solution lies in between. So we get the average of the two, which is a 25, right? We plug in a 25. So we have 30 plus 47.088 cos 25 minus 225 sine 25 cos 25. This gives us a 6.50. So again, we go to the values with the smallest minus and the smallest positive, smallest negative and smallest positive. We get those values, we get the average of 30 and 25. So the average of that gives us a 27.5 degrees. We plug it in, so we have 50 plus 47.88 cos 27.5 minus 225 sine 27.5 cos 27.5. Alright, so we have a minus 0.39. Alright, so we get the average of the two, which is nice. The solution is somewhere between 25 and 27.5, which is cool. So we can still get the average of that so that we narrow down to a solution. 25 plus 27.5 is the 2.5, and then we have the average of 26.25. We plug it in. 50 plus 40.88 40.088 cos 26.25 minus 225 sine 26.25 cos 26.25. Okay, so we have a minus 3.30. Okay, so we get the average of, again, the smallest values. Okay, there we go. So this is minus. So what are the smallest values? So the average again, so it is taking us back to, of course, the solution now lies between, let me check this again, 25 plus 27.5, 52.26.25. Okay, 50 plus 47.088 cos 26.25 minus 225 sine 26.25 cos 26.25. All right, so this one was not correctly calculated. This gives us a 2.98, right? So we get the average of the two again. Okay, so 27.5 plus 26.25 divided by 2, this gives us a 26.88. We plug it in again, 50 plus 47.088 cos 26.88 minus 225 sine 26.88 cos 26.88. So this one gives us a 1.26. So we get again average of the smallest values, negative and positive. So 27.5 plus 26.88, average of that, we have a 27.19 degrees. So we plug it in. So it's 50 plus 47.088 cos 27.19 minus 225 sine 27.19 cos 27.19. Okay, so we have a 0.43. Okay, so again the average of the two, these are the smallest values. So 27.19 plus 27.5, average of that is 27.35. So 50 plus 47.088 cos 27.35 minus 225 cos 27.35 sine 27.35. So this one gives us a 0.008, okay, which is a 9. All right, so this is a good error. 1, 2, 3. Okay, this one is a good error. You can still check out this. You get the average of the smallest values of 27.5 plus 27.35. Average of that, we have a 27.43. Okay, so we have 50 plus 47.088 cos 27.43 minus 225 sine 27.43 cos 27.43. Okay, so we get a minus 0.20. Okay, we get the average of the two, 27.35 plus 27.43 divided by 2. This gives us a 27.39. Okay, so we have a 50 plus 47.088 cos 27.39 minus 225 cos 27.39 sine 27.39. So we have a minus 0.097. Okay, so of course this still remains the smallest value. You can we know that the solution lies somewhere between the two. You can still get another value there. Check out this. You can get this, the smallest values. 27.35 plus, we know that the solution is somewhere between there, plus 27.39 divided by 2. This comes down to 27.37. You can check that one. So 50 plus 47.088 cos 27.37 minus 225 sine 27.37 cos 27.37. So we have a minus 0.044. All right, so again, we get the average. So this has the smallest value. All right, this so far has the smallest value, which is this value here. Okay, and we know the solution lies somewhere between 27.35 and 27.37. Okay, all right. Of course, you would say, why not try? We can again try this. We check the next one, which will be 27.36. Okay, 27.35 plus 27.37 divided by 2. We have the last one in between the last value that we can test here. In between that, what do we get? So 50 plus 47.088 cos 27.36 minus 225 sine 27.36 cos 27.36. So we have a minus 0.018. Okay, so that is still the lowest value. Okay, so therefore theta is just going to be approximately equal to 27.35. Okay, so that is the smallest value that we can get using this particular technique. And I think this is about it. We found the smallest value, which is 27.35 for the first case. I hope this video was helpful, and if it was, give me a thumbs up. I like my video. Continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.